So our ignition system is really unique in that it only makes as much voltage as it needs to complete the electrical circuit. And my ignition system consists of a primary low voltage circuit, which uses system voltage, and a secondary or high voltage circuit that uses thousands of volts. And that is the circuit that actually ignites the air fuel mixture. So when we look at ignition systems, whether I go in my Wayback Machine and start off with my 1955 Chevy, or whether I'm looking at a 2021, all of these systems have a primary system and a secondary system. So the key in the start position, an electrical connection is made between the vehicle battery and the primary windings of the coil. As the engine is cranked, a switching circuit turns the primary ignition coil circuit on and off. High voltage delivered from each ignition coil to each cylinder, if I have multiple coils, or from one ignition coil, if I'm sharing it with everybody. As the high voltage pushes current across the spark plug, the air fuel mixture is ignited, causing the power stroke. So what's interesting about the ignition system is we don't fire the spark plug when we turn the ignition system on or when we turn the primary system on. We fire when we collapse it, when we turn it off. So it's kind of unique. We actually turn it on, and then when we turn it off is when the spark plug fires. So it's that really created a lot of confusion for me when I was learning this. And that happens because we build an electromagnetic field and then we collapse the field. And when we collapse the field, we get what's called an inductive spike. And that inductive spike is channeled through the secondary side of the coil. And that's what generates that high voltage starting with only 12 volts. So if I look at a basic system here, this is a contact breaker system or a points ignition system. And we're going to drill into each of these systems separately and break apart all the pieces. But this is just kind of an overview. So I've got my battery, I've got an ignition switch. And so we're in the Wayback Machine. I'm actually pulling power through the starter solenoid. So we have power going to the positive side of the coil. The negative side of the coil is attached to a switch, which we're going to call the points. When the points are closed, the circuit is flowing current. When the points are open, the circuit is no longer flowing current. So every time the points would come by one of these high spots, the points would open, would collapse the circuit, and now that inductive voltage would actually come out the secondary lead, the high voltage of the coil, comes over here to my distributor. And inside my distributor, I would have a distributor rotor that is spinning around, and it sends the spark to each of the cylinders in order. And then the spark comes down through the spark plug to ground. So my coil only makes as much voltage as it needs to get from here to ground. So if, for example, I had a spark plug and I bent the ground electrode so it was touching, my coil would make almost no voltage. If I have it a big distance away, the coil is going to make as much voltage as it can till it is max to jump that distance. So I know, Tim, you talked about your coil jumping quite a ways. So your coil was generating a huge amount of voltage to bridge that gap, which is hard on the coil. So if I take that and now I just ground that, so it's just touching ground, now the coil has to make almost no voltage to complete the circuit. Very easy on the coil. That's why during testing, we normally ground the coil or we throw a calibrated tester on it. We don't want to just leave it out and let, can you do 60,000, 70,000, 100,000? Oh, we killed you, sorry.
So I got one of those testing,
yeah,
that you ground.
They're pretty slick.
Yeah.
It's also nice because you can do a lot of diagnostic by yourself because you can hear that thing snapping.
Sir Brian?
Yes.
What is the sequence of sparking the cylinder?
It is called the firing order.
Firing order?
Right. So the firing order varies by vehicle, varies by engine. And the firing order, if my distributor rotated this way, my firing order might be 1, 3, 4, 2. It'll go back 1, 3, 4, 2. So that is based on the piston's position. So we talked about that a little bit. How, like on a 4-cylinder engine, I'd have 2 pistons at top dead center and 2 pistons at bottom dead center at the same time. One of those at top dead center is on the compression stroke. The other one's at the exhaust stroke. So if I'm firing cylinder number 1 here, that would mean number 1 would be at the compression stroke. So number 4 would be on the exhaust stroke, or 180 degrees of cam timing out. So that's why it's because the distributor is timed to the camshaft. So the distributor is going to make 1 revolution for every 1 revolution the camshaft turns around. So the distributor and the camshaft are 1-to-1. Remember, my crankshaft turns around twice for every time my camshaft goes around. So in order for my distributor to go all the way around, my crankshaft has to turn 2 complete revolutions, or 720 degrees.
Okay, thank you.
You bet. So the next evolution we had, and we saw this on some import vehicles in the late 60s, early 70s. By 1974, we'd completely gotten rid of points on domestic cars, although some Asian imports used it up to 1980. And what we did is, instead of having a points and condenser, we put a electronic module there. So now I'm going to use a sensor to tell where the distributor is, and we're going to use a computer to do the switch, or a module to do the switch. Our distributors stayed basically the same, except for it's made to handle more voltage, because one of the advantages of a solid state switching is that it creates higher output voltage than a points and condenser style. So our coils got upgraded a little bit. We still had the ignition switch, and I no longer need that ballast resistor, because we use the ballast resistor for point systems to keep from burning up the points by dropping the voltage going to the points. No longer an issue. We don't have points. We're switching everything with solid state. So again, very similar in look. Our next big change is we went to a distributorless system, often called waste spark. And on this system, I still have some kind of signal, crank sensor, cam sensor, or both. I still have an ignition module. I no longer have a distributor. And now my coils actually each fire 2 spark plugs at the same time. So it fires 1 and 4 at the same time, and it fires 2 and 3 at the same time. So now we're actually firing the spark plug on top dead center of compression and top dead center of exhaust. And we'll get more into how that works. But this was the next evolution. We saw this in the late 80s. Mid to late 80s is when we went to started seeing this. This is still used by some manufacturers today, unlike distributors that are completely gone now. And what most cars use today is what we call coil on plug, or COP ignition system. And this is where each coil goes to 1 spark plug. So since heat damages coils, I'm firing my coils 1/4 of the time now if I got 4 coils. If it's 8 coils, 1/8 of the time, right? Because before that, coil had to fire for every spark plug. Now, I only need to fire when it's number 1's turn. So a lot less wear and tear, also greater control. We're still using sensors. Unfortunately, they only do 1 sensor with this system. I'm actually have to use 2 sensors. I have to have a cam sensor and I have to have a crank sensor. So we are going to use both sensors for this. Unfortunately, the book's diagram just showed 1 sensor, which is not possible with this system. This system requires 2 sensors to get that trigger speed, but we're still, now on this system here, we'll find out that my ignition control module can be in the computer or it can be in the ignition coil, depending on how it's designed, and I'll show you how to tell the difference. So I've got some information in the notes. I got a lot of notes in this PowerPoint presentation because it's a big presentation. I'm not going to use all the slides. A lot of them are step-by-step instructions how to do different tasks that the book has. Some of it are tasks we just don't do, and I'll explain why we really don't do them. But the tasks are in the book. So Let's start off with looking at our primary and secondary circuits, since all 4 systems have both of these circuits. So what I'm going to do is I'm going to start off with what everything has in common. And then I'm going to get in the Wayback Machine and show you how the circuit worked when we had a mechanical switch that opened and closed the circuit. And then we're going to go through the evolution of the ignition system and show you how we replace these mechanical things with electronic things slowly as we evolved each of these systems and how these systems work. And if I'm looking at a modern system, I need to ask whose job it is to do what. I need to understand who's my trigger, who handles the switching, where's the coil, where's the spark plug, those kinds of things. So if I understand whose job it is to do what, then I can test them because I know what they're supposed to be doing. So for example, if it's a trigger that's supposed to be telling the computer the engine's going around, that's a camshaft sensor, crankshaft sensor. So that's going to either be a Hall effect or a permanent magnet sensor. Well, does it have 2 wires or 3 wires? First clue. Based on that, we've already learned about sensors. I can go test to see if that sensor works, can I? Because the ignition system will never generate a spark if it doesn't know the engine's going around. So if it does know the engine's around, the next question, does the switch know the engine's going around? So that might be my computer, might be an ignition control module, might be an ignition coil with it built in. But what I'm looking for is there a signal going to what's supposed to switch? If it's getting a signal, the next question is, does it switch? Well, I can check that with a scope too. So I break it down this way because it's really important for diagnosis and understanding. A lot of these components on modern vehicles are fairly expensive, and I see people guessing a lot. Well, let's order an ignition module. They go bad all the time. Well, let's order a crank sensor. They go bad all the time. Let's order a cam sensor. They go bad. Right. So the list goes on. And what inevitably ends up happening is good parts are taken off, bad parts are putting on, and there's a lot of new parts on a car that still doesn't run. And that's about the time it gets towed into the shop. So it's much easier if we just ask what each thing's supposed to do and then test those things. So the induction coil converts relatively low voltage to high current flow into very high voltage with very low current flow. So one reason why the ignition system didn't kill me when I was doing the power balance test is because there's almost no amperage. So even though I'm getting hit with 30,000 plus volts, which on the 7th or 8th time, I'm definitely feeling, there's not enough amperage to kill me. Now, if I had a pacemaker or something like that, it might be a different story. The low voltage side is the primary circuit. The high voltage side is the secondary circuit. A problem on the primary circuit will affect the output of the secondary circuit. So in other words, if my battery has 12 volts cranking, I'm going to get a much better spark than if my battery only has 10 volts cranking. So even though there's thousands of volts that go through the spark plug, that voltage is generated by my primary voltage. So anything that lowers my primary voltage or affects my primary circuit is going to affect my secondary circuit. Conversely, my primary circuit also mirrors my secondary circuit. So I can actually look at my primary circuit and see when the spark plug fires and how long it fired for and all those things also, because they mirror each other, because they're tied electrically together. So all ignition systems have these parts. So I made this slide to kind of try to break down some commonality. So on my primary system, I have a trigger. I have a switching device. All systems have this. I cannot operate an ignition system without a trigger and a switching device. Then I need an ignition coil, and my ignition coil is the one component that is shared by both my primary and my secondary ignition systems. It's my crossover component. All systems have some sort of wire to connect the ignition coil to the spark plug, and all systems have a spark plug. So my coil wire may be many feet long, and maybe a simple coil boot that's this long that's actually part of the ignition coil and not sold separately, or it may be sold separately. But there is going to be some kind of conductor between the secondary output of the coil and the spark plug, whether it's a couple inches long or a couple feet long. So every system is going to have these parts. So if I'm looking at a vehicle, I need to ask myself, well, who's the trigger? Who's the switch? Where's the coil? Those kinds of things. And by understanding that, and now I know that we have these things, the next thing is to learn what the job of each of these things are and actually what kind of information they're sending, because then I can diagnose the system. Now, the book put in these charts on the table. It kind of goes into some of the primary components on each. I did think it was interesting that they didn't include the battery with the breaker point system, but they did with everyone else. Which again, the battery is part of the system. They use the word capacitor here. Capacitor and condenser are the same thing. So on ignition system, we call it a condenser, but it is a capacitor. So sometimes there's some confusion on that. The ignition coil is part of which ignition system?
Both primary
Both primary and secondary.
and secondary.
You got it, number 3.
Yeah.
It's our crossover component. So the book talks a little bit about Faraday's law. I don't test you on it. I really don't care about it. Most automotive ignition systems use ignition coils that operate on the principles of the induction coil. Automotive induction coil steps up nominal battery voltage from 12 volts up to as much as 100,000 volts. Faraday's law states that relative movement between a conductor and a magnetic field allows 4 ways by which voltage can be induced into a conductor as an alternator, generator, self-induction, or mutual induction. The value of the voltage from the 4 ways of voltage induction depends on the density or strength of the magnetic field, the number of turns or windings in the coil, and the speed at which the lines of current or force are cut. So as we look at this, that's why you can buy high output coils. So they do make racing coils, high output coils. You see them, hey, this makes more oil. Well, why? Because we're changing the magnetic field. We've added more turns to the wire, right? So I'm going to get a bigger out. The speed at which the force lines of force are cut is why an electronic ignition system will generate more secondary voltage than a mechanical system. Because if I'm mechanically opening and closing these points, that's going to take longer than a transistor. So since the transistor can cut the circuit quicker, we get more voltage out of it. That's why electronic ignition systems put out more voltage. The primary
Brian?
yes.
You said the number of windings. How about the size of the winding wire? Does it also?
Yeah, the size of the windings, the primary windings are bigger than the secondary windings. The secondary windings are very, very fine windings, where primary windings are bigger. They're still not what we would call big wires or heavy wires, but they're much bigger by comparison. And I got a cutaway coming up to kind of show that. So I have to use very fine wire for my secondary in order for it to, because I have thousands of turns of it. And so I'm doing that in order to generate that high voltage. So we do, but yes, they can manipulate this. How big do I want it to get? Because then we get into size and weight issues and other things. And how much voltage do I really need?
Okay, thank you.
Mm-hmm. So the maximum value of the secondary voltage is partly determined by the ratio of the number of turns in the secondary windings to primary windings and the value of the self-induced voltage in the primary windings. So there's also a ratio between primary and secondary. So there's some engineering that goes in here. We're not just wrapping some wire around, although we can do that and create the field. And Frank's done this in his class on different things, but there's also a ratio involved. So there's some engineering to get exactly what we want out of an ignition coil. So can I build an ignition coil that puts out more spark? Yes. Is that coil going to last as long? Fair question. Do I only need to go 500 miles making left turns, or do I want to go 200,000 miles? Am I willing to give up a little bit of that peak performance to get that longevity? So there's obviously, it's just like anything, there's that sweet spot. The required voltage is the amount of voltage required to initially get current to jump the spark plug gap. The available voltage is the maximum amount of voltage the ignition coil can put out. So in other words, I may only need 10,000 volts to jump the gap of the spark plug. If I only need 10,000, my coil is only going to make 10,000. However, a coil on an electronic system needs to be able to put out a minimum of 30,000 volts, or there's a problem with the system. So I don't need 30,000 volts all the time. But when I have high demand, like I accelerate, or when I'm first starting the car or things like that, I may very well need that 30,000 volts. So that's where we test a coil's potential with the coil tester like you got versus does it make a spark across a spark plug? In the old days, we weren't as scientific. We would hold a screwdriver up to a piece of metal and we'd look at a spark and go, what color is it? How good does it look? How far does it go? And try to make a decision of, I think this is okay. And hard to believe that sometimes we went around in circles trying to fix a car. Because what's okay here might not be enough or be okay inside a combustion chamber under pressure. Because as we increase pressure, we increase the density of the air fuel mixture, which increases the resistance. You need more voltage. If it's a lean mixture, you need more voltage because a lean mixture has fewer hydrocarbons in the mix. Therefore, the resistance inside the combustion chamber is higher. So remember, fuel is a hydrocarbon. Carbon is a conductor. So if I have less hydrocarbon and I have more oxygen, which is volatile, but nitrogen, which is inert, I've increased the resistance inside the combustion chamber. Therefore, a lean mixture takes more voltage to jump the gap and more voltage to continue the burn. Higher required voltage and lower available voltage will prevent the spark from occurring, causing a misfire. Over time, the required voltage will increase while the available voltage decreases. Reserve voltage is above the required voltage used to prevent a misfire. So this is really confusing how they put it. But what they're saying is, if I have 10,000 volts and I'm jumping my spark plug all day long with 10,000 volts, and now we have a problem. You were supposed to change the spark plugs. And so instead of jumping this far, now we're having to jump this far because you wore that spark plug out. Well, now I need what? More voltage to jump that bigger gap. So there's one example why I need that additional voltage. Another example would be, I'm driving my car, la-di-da-di-da, and I pick up 3 friends. Now my car weighs more. Now when I accelerate, I'm going to need more voltage to jump the gap to provide power for this car to move forward without misfiring. So ignition misfires are normally felt right off idle, right when we first crack the throttle and start to accelerate under a heavy load is when the ignition system normally breaks down first. It's not going down the highway at 70 miles an hour. It's not going up a hill, although it can be up a hill because, again, that's a load. Most common is right as you start to accelerate, right as you start to give it gas.
Brian,
Yes.
when it says the required voltage will increase while the available voltage decreases, is that because the spark plug is worn out? That's why
It can be. It can also be due to a mixture issue. It can be due to a bad spark plug wire. So it could be due to a coil that's wearing out. There's a lot of things that can cause that.
Okay, thank you.
So this is an ignition pattern. And so here we're looking at one cylinder on the top On the bottom, we're looking at several cylinders. And so you'd want them all to be the same, ideally. So this is what we call a parade pattern. And we would look at the firing voltage, and the firing voltages should all be the same. If they're not, that would get our attention. That was the easiest thing to see on an ignition oscilloscope. Because again, we're looking to see if they're all the same. From there, there's more subtleties that we would look at. But if you had a car that's misfiring, that was the first thing you did back in the day, and you'd see which cylinder it was. So this is how much voltage it takes to jump the gap of the spark plug. My burn voltage is the amount of voltage used and the amount of time that that spark stays continuously across the spark plug gap. Once it does that, we have some 3 to 5 coil oscillations, which is kind of the death throes of the coil. In other words, I need so much energy to keep going across that gap. I can no longer go across the gap, but I still have this leftover energy. It's just not enough to get across the gap. So we see these coil oscillations, and I actually want to see them. This is my reserve capacity of the coil. So if I don't have these coil oscillations at all, that's a sign that my coil's bad, or very likely bad. I need to look at what my firing voltage is and my burn time. Because if my firing voltage is 50, 60,000 volts, that would explain why there's no oscillations. We've used everything we have just to get across the gap. So you've always got to put it in perspective. But if the other things are within reason or low, for example, low firing voltage, short burn time, and no coil oscillations, that's a bad coil. Then we come along, and then we're going to basically complete our circuit through the primary windings. We used to call it points close. And we start flowing current through the coil. This is a later system. They started doing this in the 80s, called current limiting, where they didn't want to flow too much current through the coil, so they would back off how much current they're flowing partway through dwell. I wish they had not put this in here in the book stuff, because most cars don't have that. It's a little confusing. So if I look here, I can see where my voltage is for each cylinder. And I can see here, there's normal, there's normal. This one's high because it's an open circuit misfire. So in this case, if I have if my gap is too far, my mixture is so lean that like there's no fuel going in there, bad spark plug wire, those kinds of things, I will see high firing voltage. And if you notice, when we have high firing voltage here, I have low burn voltage here. See how short that is compared to these? See how this is much longer, where this is much shorter. So you think about it, it's like a string, and you put a 90 degree in the middle of it. As I bring up my firing line, my burn time gets shorter. As my firing line comes down, my burn time can get longer. So it's one of those. So my firing line and my burn time are exact opposite of each other. So as I use more energy to jump the gap, I'm going to have less time that I'm going to be able to push energy across the gap. On the other hand, if I use less energy to jump the gap, now I'll spend more in time crossing the gap. So if we look here, here's a shorted spark plug, very, very low. It doesn't take a lot of voltage to go across a wet spark plug or a bunch of carbon, but look at how long that voltage is able to go across, right? So a smaller firing line, longer spark line. So those are, as one gets long, the other one gets short, and vice versa. So this is what they talk about, the difference between required voltage and available voltage. So my available voltage on this is 30,000 volts, which is very low by today's standards. The required voltage right here, I'm about 15,000 volts, which leaves me that 15,000 volts in reserve. So when the spark plug is open, I'm going to hit that maximum voltage trying to ignite that air fuel mixture. On the other hand, if I am fouled, if there's a short there or the wire is jumped to ground, then it takes almost very little voltage to jump that gap. We're just going to flow a lot of current to ground. So we'll look at some, I have some other pictures that dissect this a little bit better than the book did here, but you get the idea. So in the old days, this was the go-to tool for diagnosing how a car runs. And that was true really until the 90s when waste spark became very common. And to hook a scope up to a waste spark system was just not time efficient at all. We used to be able to get this pattern by hooking one lead on. Hey, all I got to do is hook onto the coil wire. I've got all this information. So if I want to know what cylinder it is, then I'd hook up another one to let me know where number one is and so on. I could get more information. But, so even two leads going around a coil wire and the spark plug wire going to number one spark plug, I got all this information. So you can see why shops, decent shops use scopes a lot. There were shops back in the 70s and even 80s and into the 90s that didn't own a scope. So they're trying to fix people's cars without the tools. No different than today, because these scopes were pricey.
Is that just using one of those inductive type of leads? You just put it around the wire and it senses
Yep.
the current, and then it registers as voltage on the scope?
Yep.
Okay.
Yeah, that's what we did back then because everything had spark plug wires. So it was very easy to do. So I still have equipment. I still have an ignition scope here at the house. I still have the ability to do that. But fewer and fewer cars I can do that on.
Yeah, you want to sell one of those? I got to crack these on. Hey, what's a misfire sound or feel like?
A misfire, by definition, is any time we're not completely burning the air fuel charge that we put in the cylinder. So it can be felt as like a popping sound out the back, like we hear pop, pop. Like I fired up my Harley this weekend and I hadn't fired it up in over a year. So I had to get some fresh gas and all that. And I first fired it up, I was getting some popping out the tailpipe and stuff. You could hear it not running right, and kind of got some good gas through it. And then I started a little bit of detonation when I first cracked the throttle. So I had some additive in it, better gas, went out, ran the stuff through. And by the time I got back, it was happier. The most common thing we feel on a car with a misfire by the time it comes into the shop, other than the flashing check engine light, is when you're first taking up from a stop, especially going up the hill, you feel a little bit of shaking, kind of just shakes and then it kind of goes away. Or if you put your foot to the floor, it seems to go away, but on light throttle, you get some shaking out of the car as you accelerate. That's normally an ignition misfire. You can get fuel misfires also, although technically, yes, it's a misfiring cylinder, but it's not a misfire because you're not putting any fuel in there. I mean, it's one of those kind of, you can make it overly complicated. But misfires can be caused by fuel, ignition, or compression. Any of those will cause a cylinder to misfire. So like my Jeep, I was up here with Jessica and she moved it. She didn't notice it. I hopped in it. I could feel it misfiring consistently, but not every time. It just, so a lot of times people don't know, they think the car is idling rough, but it's actually only running on 7 of 8 cylinders. That's why it's idling rough, because it's not even, but they're not picking that out. So part of it's looking at the exhaust, because the exhaust should have a nice even cadence to it. So if it doesn't, that's a sign that there's some misfire going on. And certainly how's the car feel? Is it smooth? How does it, so for what we do, if I suspect an ignition misfire on a car, especially if it's idling smooth when I get into it, what I'll do is I'll put my foot on the brake, put it in drive, and put my other foot on the gas while my foot is firmly on the brake. So the car's not going anywhere, but I'm going to rev it up to about 1,500 RPM very slightly, just slightly give it some gas and see if the engine starts shaking. And you'll actually feel a miss in it. And it's very, very detectable because, again, as we put it under load, I'm stressing that ignition system. So if it misfires when I'm doing that and it's idling smooth, 99.9 times out of 100, that's an ignition miss. Because a fuel miss isn't going to do that. Fuel misses, we get surges going down the highway. We get some weird things going up a hill. If I have an injector that's bad altogether and not put any fuel in the engine will idle rough, but as soon as I rev it up, it runs smooth. And the reason for that is we're spraying the fuel in to behind the intake valve on a port fuel injected engine. And so even though I have one injector that's not spraying any fuel in, as I raise the engine up, there's enough turbulence in the intake manifold that the fuel from the other cylinders gets mixed in the air and it hides the bad cylinder. So a bad injector, you'll feel a dead miss at idle. It's running on, 3 cylinders or 5 cylinders or 7 cylinders, whatever. But you rev it up, it feels smooth, and you drive it down the road, it doesn't feel that bad. But it's missing at idle, it's shaking at idle. And that's very common of an injector, where an ignition problem, if it's missing at idle, it's missing all the time, or it's fine at idle, but only misses when you brake torque and start coming off idle. So that's, that's a way. I mean, I could do all that with a scope, but that's a way today on cars. I hop in and drive it. How's the car run? What's it doing? And it's a learned thing. One way we learned is you got the spark tester, take one of the spark plug wires and throw it on the spark tester, get in the vehicle and see how it runs. That's a misfire, right? I mean, so we learn by feeling. And what I can tell you is, from doing a lot of teaching, students don't necessarily notice that. They put cars back all the time that aren't running on all the cylinders, because it idles are rough, but we put everything back together and we just park the car, and I get in it to move it. It's like, this thing's not running on all the cylinders. Who put this thing away? And I'll ask other instructors sometimes and go, how'd that car? Oh, it ran fine. Really? That ran fine? So a lot of instructors, if they haven't spent time as a drivability tech or enough time in the shop, they can't tell when it's misfiring either. I found out the hard way. So, a lot of instructors are just completely don't even notice it. So it is a felt thing. But like on my Jeep, and I do have another video coming up on it in a couple of modules, where I actually diagnosed the misfire, and I find that it's only misfiring about 1 out of every 4 times on the cylinder that's misfiring. So I have one cylinder and it's only missing at idle, at low idle, about 25% of the time. But I was able to figure it out and figure out what's wrong and everything else. But I felt that because I've just been doing it a long time. But if a car's running rough, that's kind of the first clue. I mean, you need to at least suspect that you have a cylinder misfiring if the car's not smooth. I mean, there's other things that can do that, things out of adjustment or things that affect all the cylinders. But especially if the car's running good, it's been running good, and all of a sudden it feels a little rough, you got to at least ask the question. And then if it feels a little rough, you brake torque it. Now I got a lot rough. Okay, I have an ignition problem. It smooths out or doesn't feel good. Okay, do I have some fuel going on? Especially if I'm looking at older cars with a carburetor, I could have a carburetor that's slightly out of balance. I could have one side of the carburetor that's running too lean, causing some misfire. So I mean, which again, once I come off idle, I'm no longer running fuel through the idle jets, and then the problem's hidden. So I could have an idle jet problem. I mean, so again, it kind of varies by the type of vehicle. But those are the questions I ask. If it's running rough, does it run off idle? Does it run rough when I'm brake torquing it? How's it go down the road? Because that kind of helps you figure out what could and couldn't be the problem. I know it was kind of a long and convoluted non-answer, but it's it is kind of hard to describe, and it's easier to show.
That just means it was a good question. That's all.
Yeah,
It's clear
it
as
was
mud.
Clear as mud. All right, starting off early in the mud patch. Okay, so components common to all ignition systems. Most ignition systems include battery, ignition switch, ignition coils, high tension leads, also spark plugs and spark plug wires. So again, the book loves to start at the battery. Is the battery part of the ignition system? Well, certainly during cranking it is, because if I have low battery voltage, I'm not going to get a good spark. But we know once we start the engine, now the charging system's taken over. So why didn't they list my alternator here? Since my alternator is providing the power, right? So, I mean, we can get as convoluted as you want. I tend to stop really I might go to the ignition switch, but a lot of times I'm just power from ignition switch. You know, I mean, we're really, let's look at the system itself. We know it's getting power from the battery. So battery is used to start the vehicle, provide electrical power to all loads, and the ignition switch is used to connect and disconnect the ignition system to the battery. Ignition coil is needed to amplify my battery voltage, and the high tension leads transmit that high voltage from the coils to the spark plugs. Spark plugs provide the spark to jump within the combustion chamber. So the ignition switch here, and I included this because there's always some confusion. The ignition switch has several positions. We have a lock where it's off and you can't turn the steering wheel, or you're going to turn a little bit and it's going to stop. Off just means it's off, but you can still turn the steering wheel. So electrically, lock and off are the same from an electrical standpoint. The only difference is the mechanical lock on the steering wheel. Accessory means that I'm powering up things like the radio or windows or things like that, but I'm not feeding any power to my ignition system. On or run means I'm feeding power to my ignition system along with everything else. Start and crank means I'm feeding power to the ignition system, and some older vehicles, it meant I disconnected power from accessory. So the radio would actually go out when you turn to the start position. Your radio, other things would turn off while you were cranking the vehicle. And that was an attempt to have the maximum amount of voltage to crank the vehicle and, you know, get it started. Batteries have gotten better. Starters take less energy. So we don't see that today. But it was not uncommon on old cars. So if I use a phrase key on, engine off, that means my key is in the on or run position, but the engine is not rotating. When we use the key on, engine running, or KOER, that means that the key is in the on or run position and the engine is rotating. So many tests, they will tell you to perform in the key on, engine off position or the key on, engine running position, as we do different tests on the automotive engine. So those are the two things. The other reason why we use an accessory position, which is going away now, by the way, on some of these new push button cars, because the computer is now controlling the current flow through the ignition circuit. So it doesn't matter because it's not going to flow it till it sees the engine rotate. On older vehicles with ignition points, if the points are designed to flow current through them, but only for a short period of time. So if I turn my key to the on position and my points happen to be closed and I sit there and listen to the radio for a half hour, my car will probably not start because I've just burned up the points. So we had an accessory position so you could listen to the radio, not flow any current through the ignition system, which would not burn up the points or overheat the coil. The other issue we had with coils is coils had oil inside them and the oil was there for cooling. If we flowed current through the coil too long, it would get too hot. It would boil the oil out of the coil, ruining the coil. So if you ever see a coil leaking, it can be from physical damage, but a lot of times it's someone left the key on the run position and got it too hot, and now the coil's junk. So again, kind of going in the way back machine a little bit, but these are issues that we had on vehicles, you know, really up until the 70s. And there is still a lot of old car hot rods and people like that stuff. So there is still these systems out there. The key itself consists of two main parts: a mechanical key, which we talked about, this actually turning the lock, and a transponder, which gives it permission to actually turn things on and activate things. So we talked about that already in our security system. And many automatic transmission vehicles today, the ignition switch also has transmission shift interlock connected to it. So you can't shift it out of gear unless the key's in the ignition. So this goes back to our electrical, and we talk about vehicle theft protection. So here's our ignition coil. So my ignition coil gets battery power at positive terminal, and we switch the negative terminal. And here is my secondary output, which is my high tension tower. And so here you can kind of see the ratio they're using in the book, 200 turns of heavy wire, and heavy being relative, compared to 20,000 turns of very fine wire. That's a big ratio difference. And it is done around an iron core. So we're generating that electromagnetic field. Excuse me. If you notice, they are connected right here. So I have power comes in the primary, it wraps around, then it bridges off to secondary and goes to the negative. Well, when I connect this to ground, and this is to power, that means this is my load, this coil of wire. So that coil of wire is what's keeping all the smoke from coming out. So this is going to heat up. Now, when I open this circuit up and I no longer am grounded, it creates an inductive kick. Now, this inductive kick has two choices. One, I can go back this way, or I can go this way. And it goes through the fine wire up through the 20,000 turns and out the high tension lead. It's really kind of cool. I mean, I've been working on these things for 4 decades, and as far as I'm concerned, they're still magic. It just blows my mind. It's like, why does that work? I know how it works. I know it does work. I'd have never invented this in a million years. And I'm looking at it even now going, why does that happen? Why does it choose left instead of right? I mean, so I can test these. I've replaced a ton of them, everything else. But I'm here to tell you, if you're confused, 40 years later, these still confuse me, even though I understand how they work, because it's like magic. It's like, really? This actually does that. So, I mean, I struggled for years trying to do it, and it didn't help any because the old school testing method for these is you would measure the resistance between the positive and negative terminals, and there's a specification. And then you'd measure the resistance between the high tension lead and I think it was negative terminal only. And you would measure that against specification. So you'd measure, because that way you're only measuring your secondary resistance because you're where you're tied in. So you go between the high negative and high tension and between negative and positive, and you had specs for the primary side and secondary side of the coil. They still publish those specs, and you used an ohm meter. The issue is that the coil could ohm out bad and not be the problem as to why the car didn't start. So you just put a new coil in, the car still don't start. Half the time you ohmed out the new coil you got from the parts house, and it was as bad as the one you're taking off. It wasn't in spec either.
Question.
Yes.
Sir, the picture is very clear, but you are right. It's showing like a magic switch. But when it heat up, for heating, you need a resistance.
Right. And you have resistance in both of these wires.
So this is enough to heat the...
Yep. Absolutely. Absolutely. So there is resistance in each of these, and that's why there's a specification we would use.
Yeah.
Sir Brian, are the
Yes.
windings in the same direction? The
What's
wires?
that?
Are the windings wound in the same direction?
In the picture, they kind of appear to be. I don't know if they need to be.
It doesn't affect
Yeah, great
the
question.
effect.
I don't want to give you the wrong answer, so I'd rather tell you I don't know because I've never thought about it. You're the first person that's asked me. It's a great question. It totally makes sense now that you bring it up, but I've never thought about it. Again, these are a sealed unit. We never open them up. They're either good or they're bad. And as I was saying, back in the 80s, we did resistance testing with these, which I don't think, I mean, everyone had one in the class. We hooked up ohm meters and we did the whole exercise. And that, other than letting us know things are connected inside and has resistance, it really didn't help us understand the magic so much. We don't do that anymore. And we haven't ohmed out coils in the industry for 3 decades plus, because coils would ohm out bad and work fine. And you had coils that were within specification that wouldn't make a spark. So I don't know if the pixie dust fell out or what it was, because they were in specification, but they didn't work. So today we test these all with a scope. And if I don't have a scope, there's some tricks I can use to kind of see what's going on. So for example, we know this has to have power. We know this gets ground and then doesn't get ground. So the ground has to be on, off, on, off, on, off. And we know if that happens, I have to get spark has to come out of here or it doesn't work, right? It's an input and output. If I'm switching the primary and nothing comes out the secondary, are we all good that the coil's bad? Right? Because that's the whole thing, right? Because if I'm supposed to switch the primary, right? We flow current, don't flow current, don't flow current. And every time we stop flowing current, I'm supposed to get a spark. So if that doesn't happen, is it safe to say the coil's bad at that point? So if I have power here, and in my power here, and I go from ground power there, which I can see with a test light, I can see with a DMM, I can see with all kinds of things. And yet I have no spark coming out the coil. Are we pretty good that we need a coil at that point? Right? Because so instead of using an arbitrary number of resistance to give us some information that's not necessarily accurate, why don't we just test it in a complete circuit and see if it's doing its job? Because if I have power here all the time and there's no ground here, that's the switch's problem. It's not switching. But if the switch is switching and I have power here and the switch is switching and I get ground here and I get nothing out of here, that's the coil's problem. To me, that makes a lot more sense than taking everything apart, putting it on benches and putting ohm meters on it. And I'll come back to this thought process in the complete system. So ignition systems, late model vehicles require a minimum of 30,000 volts. I've had cars that would run and not start because they don't have 30,000 volts. They didn't need 30,000 volts to run. They did need it to start. And, you know, the first time I ran into this really led me to some misdiagnostics, because I had a car that was putting out spark, but it didn't start. But if I added gas, the car would start and run. So I'm thinking I got a plugged port in the carburetor. I'm thinking, you know, so I'm kind of going down the rabbit hole on this thing, because it wouldn't start. But if I gave it gas, it would start every time. And it would run fine. You could drive around the block, ran great. And that's when I figured out you need 30,000 volts, because this coil is putting out 12,000 volts all day long. It wouldn't put out 30. And when I put a coil on it that would put out 30, that car started just fine without me giving it any extra gas. And this was back in the 90s. And that was a 3-day lesson learned. Went down the rabbit hole on it. It's the first time I'd ever seen that. I kind of, after a couple of days, I'm checking stuff, and I didn't rebuild the carburetor, but I proved it's putting in the gas that it should, but why is it not enough to start? And I mean, it was just kind of a mind puzzle. I finally said, you know what? I really think this thing should be putting out more spark. I put a new coil in it just on a hunch, put the new coil in, the new coil kicked 30,000 volts, and that car started every fine. And that proved to me that in spite of what you'll see some places, any electronic ignition system should put out 30,000 volts. And Tim, did you have something?
Yeah, you caught me yelling at my kid. Sorry.
Oh.
Not yelling. I wanted to see if I understood that from what was happening. So basically you richened the mixture, right? Which decreased the resistance, which meant your required voltage came down.
Right.
Then it would run on that 12,000 volt and not need the 30,000.
Exactly. And because I understood that, allowed me to diagnose the car. So a lot of the background information in CDX, a lot of that stuff, and you're like, why do I need to do that if I'm getting the lectures from you? What's the importance of that? The importance of that is that we have a good basis. You have that education to fall back and ask questions when things don't work right. And that's where that education, I mean, the education I got when I got my certificate in automotive didn't so much help me fix cars, as it helped me learn how to fix cars over my years in industry, because I had that foundation. And I think that's often overlooked. So it's not just a matter of putting parts, it's being able to ask good questions when things don't work right. But like I said, that was a lesson I learned in the 90s and I've never forgotten. And that was contrary to what a lot of the books said. But I'm just kind of going around in circles going, this has to be it. And, you know, coil is only $100. It's like, you know what, I'm putting this thing on.
Sir Brian,
Yeah.
I am amazed at how the ignition coil can serve as a step up transformer from a 12 voltage to give a 30,000 volts.
As much as 100,000.
Oh, okay. That's
Yeah.
quite amazing.
It is
Is that-
amazing. It's basically a step up transformer. There is some slight differences. But no, it is absolutely amazing. And to think that they came out with this, over 100 years ago. I mean, it's just, I have a coil here from an old Ford and it's in a wood box. So it's actually a wooden coil where everything today is plastic. So it's really amazing. This technology and how things have changed. Scam likely. I don't think I need to talk to them. So the ignition coil operation, current flows through a switch and primary windings, creating a strong magnetic field. The iron core concentrates the strength in its field. When the current is interrupted by the switch, in this case, the switch being the points or an ignition control module or whatever, the magnetic field collapses. And this is a little confusing because the ignition switch is not the switch we're talking about. We're talking about the switch in the primary circuit. Secondary windings have more turns than primary windings, up to 100,000 volts is induced. So if we look here, high voltage shoots out the high voltage terminal, traveling through the secondary path. So here my switch is closed, whether this is my breaker points, whether it is my transistor in my ignition control module, my transistor in my computer, my transistor inside the actual coil assembly. But somewhere I have a switch that's controlling current, and that switch is attached to the negative side of the coil. My positive side of the coil is going to get battery voltage through my ignition system or, fuses and all that stuff. When the switch opens, the circuit collapses, the voltage is forced through the secondary windings, and we get high voltage out, which makes the spark plug go snap. So that's what I was saying. So we actually fire the spark plug when we open the switch. You think, oh, you turn it on and it works. No, you got to turn it on, wait a little bit, then turn it off and it works. So it's a little, which even added more to my confusion as a young man.
I am confused too.
So what is the minimum acceptable voltage for ignition coil output on a late model vehicle?
Is that the 30,000 volts?
30,000.
volts. You got it. Number 3, 30,000 volts. If we don't, and so a lot of diagnostics is not testing everything. It's proving what you don't have to test. So if I have a car that's not running right, say I have a car that's misfiring on a cylinder, and that cylinder, I figured out what cylinder is not producing power. If I take the spark plug off of that spark plug, the spark plug wire off the spark plug, or I take the coil off the spark plug if it's a newer vehicle, and I put that spark tester in the end of the spark plug or in the end of the wire coming out of the coil and attach it to ground, and I crank the engine over or I start the engine up, and there is spark jumping 30,000 volts. Does that prove that I'm getting ignition to that spark plug that's good? Doesn't that prove that my coil's working, my switch is working, everything's working, right? So I have a possibility, either I've got a bad spark plug, which is always possible because I didn't test that, or I have a fuel or compression problem, right? Because I've just proved what it's not. I don't need to go test the coil. It makes 30,000 volts. It's good. Hello. So now how do I test the spark plug? Well, I have another one next to it. So if I move the spark plug from the cylinder that's bad to another cylinder, I'm going to pull it out, look at it, and maybe I'll go, whoa, this thing's broken. But if I pull it out and it's normal, I'm going to put it in the cylinder next to it and put the spark plug from the cylinder next to it back into that cylinder. Now let's start it up. Is that still the cylinder that's misfiring, or did the misfire move? If it moved, you have a bad spark plug. If it didn't move, now I've proved it's not ignition. I'm down to fuel or compression. Well, if I pulled out that spark plug from that cylinder that's misfiring and it really smells like gas, or it's even wet with gas, does that prove we're getting fuel? Now I'm thinking I got some kind of compression internal engine problem. That could be a flat cam where I'm not opening a valve. It could be valves that aren't sealing. It could be a lot of things. But I've proved that I'm getting fuel, and I've proved that I'm getting spark, and therefore I don't need to test those systems. So a lot of diagnostics is doing quick, higher level tests that prove, does this whole system work? Yes. Okay, I don't need to test anything there. Why would I start off testing a fuse or testing an ignition switch or ohming out a coil or ohming out spark plug wires? Why don't I just go to the end of the line and go, can I have my 30,000 volts, please? If I have my 30,000 volts, everybody's doing their job. We're great. If I don't, now I need to go figure out where my 30,000 volts is. And so a lot of diagnostics is not testing everything in the car. I mean, a customer would never pay for it, and there's not enough hours in the day. So really the trick is to try to do higher level tests where I can prove big groups of things or systems either work fine, I don't need to test them, or hey, here's the system with my problem. So I'm only diagnosing one system, not a whole car.
Late model means what year? Late model.
For this example, it's anything with electronic ignition. So we're talking early 70s on up.
Oh my God. Late model means 70s?
Well, again, it's about technology, and late model vehicles, emission control vehicles use electronic ignition. I could have put electronic ignition in here, but then I get the confusion because we call electronic ignition a distributor system with a electronic ignition module, where waste spark and coil unplug, yeah, they're still electronic, but we don't call them electronic ignition. So that's why I use the term late model. Late model is, a relative term based on what system. It might be 2010 and newer. It might be 45 years ago. It depends on when the technology changed that caused this to be relevant. I mean, keep in mind, we've been making cars for 130 years.
Right,
So,
but CDX can put clearly what decades like 90s or anything. This is a problem from CDX, not from the technology.
well, no, it's not CDX, it's me, and it is the technology, because late model changes based on
Right.
what technology you're talking about. Am I talking about a late model car buying as a used car? Well, that's very different than if I'm talking about a technology used on a late model vehicle compared to
question itself. Yeah, question itself is a full confusion, and
right.
The 30,000 and 40,000, not much difference for the spark plug and high voltage.
Well, it's a huge difference. It's 10,000 volts, and we need to know what the minimum amount is that it has to put out.
Yeah.
So it can put out 40,000 or 50,000 or 80,000, but it needs to put out 30 or the car won't work right. That's why that's the minimum. So types of ignition systems. So we're going to get in the Wayback Machine. We're going to look at a contact breaker point systems used on earlier vehicles, relied on mechanical devices to create spark. Modern vehicles no longer use a distributor even. So the main difference among these different systems is the way the primary circuits are controlled. So if I look here at a breaker point system, which, like I said, Honda used this until 1980, but this is my, I say it's a 55 Chevy, but it's only got 6 cylinders. So take your pick. Could be my Buick 225 V6 here in my old Jeep, who knows? So I have our battery power ignition switch. I have a ballast resistor. The ballast resistor is on the run. The straight wire is on the start, because I want all the power going to the coil when I crank it, but I want to limit the voltage going to the coil with the engine running. So on older vehicles like this, occasionally you'd get them where they'd start, but they wouldn't run. So it starts, and as soon as you go turn the key back, it dies. Start, that's a bad ballast resistor. So if it starts but doesn't run on these old cars that use points, bad ballast resistor. So from here, we go to the positive side of the coil. The negative side of the coil goes to the points. The points have a condenser attached to it, and the points themselves are grounded. So this part of it's going to be grounded. This part is only grounded when it's touching this part. It goes through what's called a breaker plate and is eventually grounded to the engine. So this is my distributor cam right here. You can see I have 6 lobes, 1 for each cylinder. As each lobe comes around, it comes to the rubbing block of the points and forces the points open. So the rubbing block is my trigger. My points right here is my switch. Then I have my coil, my distributor cap right here. You can see the rotor inside's kind of highlighted. It goes around. I've got spark plug wires coming out to my spark plug. So, you know, my points and condenser setup, my points, the rubbing block with the distributor cam. So the distributor cam is really my what trigger. It's what tells me when to fire, because if I put that distributor in the wrong way, the cam would come around and open the points at the wrong time. So the distributor cam is really my trigger here. We need to know when we're doing it, and that information is mechanically transmitted to my switch, my points, and mechanically opens up my points to stop current flow through the coil, induce voltage into the secondary windings, and fire a spark plug. And to give you an idea of how fast this is happening, if I'm idling at 800 RPM, let's just go with idle first. That is 400 engine cycles per minute. Okay. I have 6 cylinders here. So you take that 400 times 6. That means those points open and close 2,400 times a minute at idle. Oh, now you want to do 3,000 RPM. Well, that's 1,500 cycles. 1,500 cycles times 6. We're going to open those points 9,000 times a minute. Oh, you want to do 5,000 RPM? That's 2,500 cycles, 6 cylinders. 2,500 times 6, that's 15,000 times a minute. We're going to open and close those points. Hard to believe points only lasted 12,000 miles at best. Okay. Absolutely amazing piece of engineering. Amazing they lasted as long as they did. Of course, people didn't drive as much then, but that's why people used to come in and get a tune-up once a year. Get new points in, get all that stuff. As the points wear, their adjustment will change, which affects how the car runs. It affects the ignition timing, all those things. So this is our basic system. Okay, so we got a trigger here. I got a switch. I got a coil. I've got my primary side. I've got my secondary side. So the contact breaker is a mechanically operated electrical switch. The contact points are opened by the cam lobes and closed by the spring. The number of lobes is equal to the number of cylinders, and the distributor has to be put into the engine in time with the pistons so that it's firing the spark plug at close to top dead center. So if the distributor is put in the wrong position, then it's not going to run. Most manufacturers specify the ignition rotor be aligned to the distributor terminal of the number 1 cylinder when the number 1 piston is at top dead center of the compression stroke. So here is a distributor right here. And you have a close-up of the operation. Here my points are closed, so current is flowing through the primary. So the blue part has power to it, and the lower part has ground to it. So when it's connected, it's connecting ground through here. And this isolated terminal or insulated terminal that goes through the distributor housing is where the wire that goes to the negative side of the coil is. If I look inside here, this is a little different model. It's a GM. You can see the distributor cam lobes here. and they rub on the rubbing block right up in here, which forces the points open. So here's our actual points right here. This is the points assembly, but here's the actual little points right here. And this is our condenser that you heard me talk about right here. The rotor would mount on top here. And this distributor also has some centrifugal advance weights on it that are not there. And we'll talk about those coming up. This screw right here was unique to General Motors and that it allowed me to adjust the points with the engine running. Everything else I had to adjust the points with the engine off. So this was kind of, we like tuning up GMs better than we like tuning up other things because of this. So the basic contact breaker point system consists of the battery, ignition switch, coil, breakers, capacitor, which is our condenser. You don't order an ignition capacitor, you order an ignition condenser. So, but technically it is a capacitor in the books being technical. The distributor connecting wires and leads, opening and closing the breaker switches the primary current on and off. When we switch it off is when we fire the coil. A capacitor absorbs the surge in inductive current by providing a very short-term alternate path in parallel with the opening contact. So it's kind of, if the condenser is not there, or if it's missing, the ignition system will not work. So it's a critical part. It's always replaced with the points. The spark at the spark plug needs to last for about a minimum of 1 millisecond. Many times we'll see it longer than that, but these older ones didn't make that much voltage. The condenser is made up of 2 plates constructed from narrow strips of aluminum foil and are insulated from each other by dielectric. The condenser is typically mounted either inside or directly on the outside of the distributor. So you can see here's a little cutaway of the condenser. Back in auto shop, we used to charge these up by putting the ground connection, then you attach battery power to the connector, and then you throw it to someone and have them catch it. And when they touch that lead, it would give it all of its power and it would give a pretty good shock. So that was auto shop fun. They don't let us shock students anymore. So I don't get to do that the way it was done to me, unfortunately.
No, you do it to yourself in video.
That's right. So here we're kind of looking in, and it is not happy with how it is. This is really, they're looking at coil oscillations here, and then your condenser oscillations. You're really not going to normally see condenser oscillations. This is your firing section. You see your coil oscillations after your firing section. So the book's a little off as far as what you're actually going to see on a scope. Ignition points serve what purpose in the ignition system?
Or
Really not so much the trigger.
for
They're really more of a switch.
switch.
You could argue that since they have the rubbing block on them, and which is part of the trigger and the switch, that you could argue for. But that's kind of why I pointed out the distributor cam is really the trigger, because the trigger is what really tells it when do we want it to fire. The switch just does the switching. So the best answer is really number 2, switch. That's kind of why I wanted to define these terms a little bit. So we talked about how many times this thing fires. So a 4-stroke engine, 4-cylinder engine running 2,000 RPM, 4,000 sparks must be supplied every minute, because that's 1,000 cycles times 4 cylinders, 4,000 sparks. Important to ensure the length of time the current flows through the primary windings is sufficient to create the necessary magnetic field. The condition in which the magnetic field to its maximum strength is called coil saturation. Dwell angle is the number of degrees that the contact points are close. The setting of the contact breaker gap controls the dwell angle. So if I look here, I have a number of degrees that the points are closed. When the rubbing block comes around on the distributor cam lobe, it's going to push it open and the points will open. They're no longer closed. So when you install points, There is two specifications we look at. One is a specification in thousandths of an inch, where we would take this around and we would walk this little rubbing block up on the high spot of the cam and use a feeler gauge like we use for valve adjustments and measure the gap here. Okay. And you had to have that, you set that gap to specification, and in theory, everything's hunky dory. That is the least accurate way of doing it. Okay. What we would do in industry is we use the other measurement, which is dwell. Dwell is in degrees. And in order to measure that, we would use a dwell meter. So the dwell meter would attach the positive lead of the meter to coil negative and the negative lead to ground. And we're going to measure the dwell. And so General Motors, which I remember for Chevrolet, is 28 to 31 degrees basically of dwell. So we would adjust that, and you would normally adjust it to the 31. Let's gotta do that right. Yes, you'd adjust it to the 31, because as the rubbing block wears, the points will get this wears here, and we would put lube on here. There's special grease. As this wears, the number of degrees that the points are closed. No, I'm wrong. I'm sorry. I go the opposite way. So you start at the bottom. You start at 28 because that's why I was questioning, because dwell moves up. So as this wears, your points are going to spend more and more degrees closed. So you set it at the lower end of the scale, the 28, which is why I questioned myself when I said it the first time. And as it wears, it'll wear up to that 31. And that way the car stays in tune longer, because it will wear as the car runs. Now, as you change dwell, you also change the time that the spark plug is going to get its spark in relationship to top dead center of the compression cycle. So if I set all this up, the next step we would do is check the timing and adjust the timing. So I say my time is supposed to be at 10 degrees before top dead center. As my dwell grew, as it got bigger, and it went from 28 to 29, I would now only be at 8 degrees before top dead center. As it went to 30, I would now only be at 6 degrees before top dead center. So for every 1 degree of dwell equals 2 degrees of timing. Think about it. My camshaft goes around once, crankshaft goes around twice. It's a 2 for 1. So as I spend more time closed, my timing actually retards. That's why people would come in and go, I really need a tune-up. My car doesn't seem to have the power it does. It's not running as good. Well, what's happened is the points had worn to where the dwell time had gotten longer, which also retarded the timing. So it didn't have the power it did. So if you set the dwell to 28 and you set the dwell to 28 every time you do the tune-up, once you've set the timing to be correct at 28 degrees of dwell, you never have to check the timing again. The reason why timing changes is because dwell affects timing. So if someone sets the dwell at different, or someone set timing when dwell wasn't perfect. So there are still stuff out there with points. Different equipment has points. Motorcycles use points up into the 80s. So there is still a lot of this, but it comes into the degrees. So it's really kind of interesting. This is back when we did tune-ups. This is when the difference between the person who was installing the parts in your car really made a huge difference, because there is a lot of technique to this, not just to the carburetor adjustments, but even to replacing the ignition components. And I gave you guys a few of the tricks here. The other trick is you would check this shaft and you would put your hand on it and try to wiggle it. If this shaft wiggled back and forth, the bushings in the distributor are bad and you need a new distributor, or you need to rebuild that one. Because keep in mind, you have this spring-loaded little arm always pushing on this. So therefore, your bushing over time would wear. Newer cars with electronic ignition, that's not an issue. But older cars with points, you're pushing on that, and a little bit of wear over a long time, a little bit of force over a long time wears the bushings out in the distributor. And so what would happen is if you get play in here, aside from the points wearing prematurely, they'd actually bounce, your dwell would be uneven, you get all kinds of drivability problems. So again, part of doing a tune-up back then was checking, is the distributor still good? Do the advanced mechanisms work? So tune-ups in the old days took a lot longer if you did them right. But if you did them right, your customer really noticed the difference when the car got back to them, because you've actually found all the problems that other people have just been taking their money, putting parts on and shipping the car. So which component serves as a trigger for a point style ignition?
Points. It says
No,
points.
points are the switch.
Oh,
I see Tim had it.
distributor cam.
Distributor cam. And the reason why I kind of split the hair on the points, even though we don't really see those anymore, is I just want us to get the concept of what the trigger is. The trigger is what is aligning the ignition system to the cycle of the engine, so the spark's going to get there at the correct time. The switch controls the primary current through the coil. So the dwell angle is the time that the points are closed. The magnetic field is building the ignition coil. The setting of the contact breaker gap influences the dwell angle, and on most systems, once it has been set, dwell angle remains fixed regardless of engine speed. And that is true. All systems are supposed to do that. On the old stuff, now when we went to electronic, we have variable dwell, so the computer can control it. A large gap gives a small dwell angle. A small gap gives a large dwell angle. Manufacturer's recommended gap provides the specified dwell angle for each application. Again, you know, if you don't have any choice, you can use a gap and then set the timing, but a gap is not as accurate as a measurement as using a dwell meter is, because the dwell meter is actually measuring the degrees. So a lot of times when we put points in, I just put them in so I know they're going to open and close, because I need them to open and close to get a dwell reading. Crank the engine over with the cap off, rotor off. What's my dwell? Okay, let me adjust it. Crank it again. What's my dwell? Set it at the low end, put the cap rotor on, start it up. Boom. How am I? You know, so in the GM had the advantage you could do it with it running, but it really, you know, I can do the other ones almost as quickly. GM just to let you be lazy. And I kind of spent a little bit of time on this because I've had a lot of technicians I've hired over the years, and I give them a set of points to put in, and I ask them, you know how to put in points? Oh yeah, no problem. And I hear the car out there. Okay, he's working on 7 again. Should have gotten it on the second shot. You kind of hear it again. Then you don't hear anything for a couple of minutes, and the guy comes walking in. I'm not sure what happened. I put the parts in and it doesn't start now. Okay, you never put in points before, have you? No. Okay, that's why I asked you up front if you had or knew how to do it, because I'd have come out and showed you and saved us the last 10 minutes I've been paying for. You know, as an employer, I'd rather have someone tell me, no, I don't know how to do this. Would you show me? Versus tell me yes and waste 10 or 15 minutes on the clock that I'm paying for. Because I didn't expect them to. And some of these guys have been doing it for 10 years. They don't know how to put points in. So here's our bypass circuit I talked about earlier. This is a GM, where they would run the ballast resistor bypass off of the starter terminal. They had an R terminal. Newer GM starters, since they went to electronic ignition in the 70s, no longer have this R terminal. For years, they had the R terminal and we didn't use it. Solenoids today don't even come with the R terminal on it on most applications. And, you know, you talk about, you know, we're in the Wayback Machine here. I just had a friend of mine call me 2 weeks ago, call me this last weekend to tell me he fixed the truck. Had a customer with a 1968 or 69 Chevy pickup truck. The car intermittently doesn't start and you have no power going to anything. It's already been to a couple other shops. And so I just spent $800 at the electrical shop getting new neutral safety switches and all kinds of stuff. Still has the same problem. Called me up. What do you think? I said, well, and this system no longer has points. It has electronic ignition distributor, but it's still a 69 truck that would have been wired like this. And I said, here's how this truck is wired. Go check this. Go check this. Worst comes to worst, it's a simple system. Abandon stuff, figure out where you're getting power from the ignition switch, run it through. I mean, it's just not that hard. Turns out someone had been in there and mixed up pins in a connector. But we were just talking about the R terminal on the starter motor because that still had one. And so I had a wire coming off of it. And so, some of this way back stuff, you still see this stuff in the shop. Even if it's been updated, I mean, just having the knowledge of kind of how things work kind of helps you see what people who don't have that knowledge might have done to a poor vehicle. So I've already talked about the system. So let's talk about distributors. So distributors, as they sound, they distribute spark to the spark plugs in the correct sequence or firing order at the correct time in the engine cycle. So if I'm replacing spark plug wires, I do them one at a time. Why? Because if I mix them up, the car doesn't run right. They also will house a vacuum and mechanical or centrifugal timing advance mechanisms on older engines. So we used vacuum and centrifugal advance, one, the other, or both up until about 1990. Distributor cap covers the end of the distributor to protect the components inside, also as a way of attaching our spark plug wires in order so that they can get their spark. In some applications, the ignition coil is mounted inside of the distributor. So here's a kind of a cutaway of a distributor. And we can see this happens to be a GM high energy ignition distributor on the right-hand side. This has the coil mounted underneath this black cover. And here's the wires going to the different spark plugs. And here we can see a terminal where the wire's been removed. If we look at a cutaway of a distributor, in this example, I have the distributor shaft. There's a gear on the bottom of the distributor shaft that engages my camshaft. I have these advance weights, which are my centrifugal advance, and I got a picture showing there. They have springs that hold them in. As we go spinning, they start moving their way out, kind of like going around in circles. When you're a kid and you bring your arms out, and as your arms out, they almost make you going too fast and you'd fall down because having that weight out there. Up here we have our what they call a reluctor. So this is electronic ignition distributor, not points, but this takes the place of the cam, distributor cam. Here we have the inductive sensor. So we're now using a pickup. Sometimes they call it a pickup coil. My rotor mounts right on my shaft. My distributor cap goes over the cover. This is my vacuum advance. It attaches to my breaker plate. So my breaker plate is grounded, but it is able to move. So the points would mount on it, or the electronic ignition would mount on it, and it's able to move slightly. So the distributor itself is spinning, and I can move. So if I want to advance, and the distributor is going this way, I would want to move it this way so it gets there sooner. So this will also, by looking at the vacuum advance, I know instantly which way the distributor rotates because I'm pulling it into where it's turning. So here's an example of a distributor mounted on an engine. In this case, the firing order is 1, 3, 4, 2. So the distributor is rotating and goes to the spark plugs 1, 3, 4, 2 in that order. If someone was to reverse these two, the vehicle would probably still start, but run very badly. If we put these on, if instead of number one being, where is number one? It's down at the bottom. So instead of it being here, maybe someone put it here and moved everything one square, the car would not start at all. If you mixed more than 2 of these up, the car would not start at all on a 4-cylinder. So that's why I say we do them one at a time. The tendency is, well, let me rip all the old stuff off. Now I'm going to open the box with the new parts and put them on. I do them one at a time. I might get a phone call. I might get interrupted. My ADD might kick in. You just never know. So I do them one at a time. And I still do them one at a time. If for some reason I didn't do that and now my car doesn't start, I would need to rotate the engine around till it is at top dead center, number 1 cylinder. Then my distributor rotor will point to number 1. Now that I know where number 1 is and I know what direction the distributor turns, now I could hook up my spark plug wires 1, 3, 4, 2, and the car would start again. So I can get there. I mean, you can give me a bucket of parts. I can still put the thing together and make it run. It's just how much effort do I want to do if all I'm doing is maintenance? Especially if it's an early Sunday morning or Saturday afternoon or whatever. I mean, why make it harder than we have to? So our firing order here is an example. So this happens to be a V8. My distributor rotates this way. And my firing order is 1, 5, 6, 3, 4, 2, 7 on this, and 8 on this particular engine. So different V8s, either from the same manufacturer or different manufacturers, will have different firing orders. So I know General Motors firing order, which also happens to be the same one Chrysler used on their V8s, or I should say the Chevy firing order, because Cadillac has some odd firing orders. So Chevrolet is the same as Chrysler. Ford had a couple different firing orders. I never did memorize those. That's why there's books. So don't assume you know it, just look it up. If I'm taking the distributor out, I would walk the engine around. So my harmonic band sort of lines up with 0, and my rotor is pointing at number 1. Now I can take, and now what I would normally do is take the spark plug wire off number 1 so that everything else has spark plug wires on it except number 1. And then I would take the distributor and the rotor's pointing this way. I would draw a line on the distributor shaft, or I mean on the housing and on the engine. So now I know if I go from this center to this line to here, they're all lined up. Now I'm going to take it out, because when I put it back in, I'm going to make sure it lines up the same way. So that's the quick cheat for that. And I know certain people's Broncos have a distributor still.
Yeah, but not points.
Oh, I already figured that by the amount of spark you got out of the coil.
Yeah.
So the distributor cap and rotor are part of which ignition system?
Both primary and secondary.
No, there's no 12 volts going through my cap and rotor. My cap and rotor takes the high voltage coming from the coil and directs it to a specific cylinder. So it is part of my secondary. And that's why I always ask
primary.
It's secondary. So my distributor has 2 different things inside it. It has a primary circuit that we see here, and it has a secondary circuit that we see here. Electrically, they are not connected. They just happen to be in the same housing and in time with each other. So spark timing varies according to the number of factors, including air-fuel ratio, knock detection, is the engine detonating or pinging, my engine speed, the amount of engine load, temperature, air temperature, transmission gear, and throttle position. At higher speeds, spark must occur sooner in the cycle. So on modern engines, I'm able to use all of these things to figure out where I want my ignition spark to be. So on modern engines, we use computerized timing control because I can take all these things into account. On older engines, we didn't have that ability. So on older engines, we would have to figure out, based on normal use, how much timing am I going to need based on engine speed, and how much additional timing am I going to need when someone puts their foot into the throttle in order for the engine to run properly. So we use two different types of advance. We use centrifugal advance and vacuum advance. The vacuum advance is designed really for that transitional, because it would be run on ported vacuum. So I would normally not have any vacuum at idle to it. And as soon as I start putting my foot into it, then we would start advancing timing. So my car would take off and accelerate. Once the engine's up to speed, those centrifugal weights would come out and further advance the timing. And as that's happening, I have less ported vacuum, so that's coming back down a little bit. So they would work together. So we have books that gave you your base timing, your maximal centrifugal advance, and at what RPM, and your maximum vacuum advance, and at what inches of mercury or what RPM. And we would actually test that to make sure the vacuum advance is working, centrifugal advance is working. Centrifugal advance, you can put different springs in them, so I can get more advanced sooner or less advanced sooner, different things. So we used to have a distributor machine. I used to own one. I just didn't have a place to keep it anymore. I ended up getting rid of it. For actually, we could set the timing curve of distributors on the machine, off the car, and real high tech stuff for the time. But there are a lot of things. Now, what do? We reprogram the computer because the computer does everything. So, today we think we're all slick because we flash stuff. We copy someone else's. Hey, I got this program and I got the tool and I could download this, or I bought this. So we flash stuff. In the old days, it was really the skill of understanding how things work and having the ability to go in and actually change those things. So you can see there's a lot more art, and now there's a lot more science. And to be honest, I miss some of that. Cars are so much more complicated today. And yet a lot of times I think technicians are not looked at as highly today as they were then in some ways, because some of those specialized skills were not something that you could just pick up. They were something that really, there's like I said, a lot of art to it, a lot of figuring out what does and doesn't, and how to maneuver and how to change. There's some neat stuff. So at low engine revolutions per minute, the spark does not have to be advanced off of the base setting. Adjustment must occur automatically in relationship to engine speed and load. If the time is advanced too far, knock occurs. If equipped with a knock sensor located on the engine block, it'll send a signal to the powertrain control module telling it to back off the timing. And the PCM retards the timing to decrease or eliminate the knock. Early vehicles that use distributor, base timing is set at idle speeds. Normally, there are a couple exceptions. Timing is almost always indexed to number one cylinder. Now, we're talking about distributors and timing. I don't know why the book put a picture here of a crankshaft sensor on an engine that doesn't use a distributor. So I don't know why. I just kind of left this here and just explained because it's a copy of what the book's doing. Today's vehicles use electronically triggered ignition systems, which we would use a crank sensor for. Timing is energized into the design of the engine and not adjustable unless you do programming. The components are the crankshaft position and camshaft position sensor, which are our triggers today. Ignition timing refers to the point at which the spark plug fires. On older vehicles with distributors, the base timing can be adjusted by rotating the position of the distributor housing. On newer vehicles, timing is not adjustable as it's computer controlled. Engine manufacturers include timing marks on many of their engines, and a lot of those are now used for assembly, not for timing. The two types of timing on gasoline engines are valve timing and ignition timing. Valve timing, as we talked about in the engine section, refers to the position of the valves in relationship to the piston stroke, where ignition timing is about when the spark gets there in relationship to top dead center. So if I look at my centrifugal advance unit, again, getting in the Wayback Machine, controls ignition timing in relationship to engine speed. So at low speed, the weights would be held in by the springs. At higher speed, they're able to overcome the spring and the weights start flying out. So depending on how strong the spring is, determines when and how fast these weights are going to move. We would get these in with broken springs, stuck weights. Sometimes these weights would stick out. Matter of fact, I had a car, 84 Honda, came to me because he knew he needed his carburetor rebuilt. And I said, you know, I'm not going to rebuild the carburetor. I'm going to start with a diagnosis. Well, I already know what's wrong. Well, I'm not interested in working on it unless I diagnose it. Okay. I mean, the other shop may be right, but I'm not just going to go in and start rebuilding the carburetor because you say that's your problem. Because I've learned enough to know when I put it back together and the problem's still there, then they're sure I did something wrong with the carburetor. So let's find out what the problem is. So went in, what I found out is the centrifugal advance weights had rusted in the advanced position in the distributor. So instead of a carburetor, what he really needed was a distributor. Far cheaper than the carburetor. And it fixed the car. So, but again, I think he was going to shops that didn't know there was centrifugal advance weights in there, that didn't know the timing's supposed to change or that it's controlled, right? So that's where, you know, a little bit of knowledge can be a dangerous thing sometimes. But that's why we go through as our diagnosis and we check all the different things. Is this working? Is this working? We know all this is going to affect how the engine runs. I certainly wouldn't want to rebuild the carburetor with a bad distributor. So it was worth checking the timing curve, spending a couple of minutes to do that, literally a couple of minutes to make sure that that was working right, because that would certainly cause the complaint that he had that he thought was the carburetor. End of the day, didn't need the carburetor rebuilt. And it passed smog, which is what he was trying to do.
What chapter of the CDX that is?
This is chapter 61. So centrifugal advance units, the inner shaft is driven by the camshaft and the outer shaft has cam lobes that controls the opening of the contact point. So we actually have a two-piece distributor shaft. It's not a solid shaft going up. This allows the lobes or the trigger wheel to move or advance. The relationship between the speed and advance is determined by how heavy the weights are and the tension on the springs. The maximum advance is determined by limiting the movement of the weights with slots, pins, or bushings. Now, vacuum advance is designed for transitional advance. So in other words, when I first put my foot on the throttle and I open the throttle plate to let more air in the engine, my engine's not going to speed up instantly. So until my engine speeds up, the centrifugal advance weights can't come out. We can't advance the engine. But I still need timing to advance or we're going to fall flat on our face and not go anywhere. So we use vacuum advance for this back in the day. Of course, now everything's computer controlled, but the function of the ignition advance to improve fuel economy, reduce exhaust emissions, advance the ignition timing under light engine loads and retard under heavy loads are designed to operate on one of three types: vacuum, ported, manifold, or Venturi. So we normally use ported vacuum. There were some systems that used manifold vacuum and a solenoid. And I'm not aware of any system that used Venturi vacuum as a primary source. They did use, I think Toyota used it as a retard on their late Tercels. They had three vacuum. They actually had three vacuum advances in one housing, three different hoses going to it, because it wasn't complicated enough with one or two. On older vehicles, ported vacuum is obtained through a small slit in the throttle bore located just above the throttle plate. So what happens here is as we open the throttle, so at idle, the throttle is where the dash part is. So I only have manifold vacuum, which is what we were testing on our vacuum lamp. As the throttle opens slightly, now I have ported vacuum. So I would have no vacuum at idle unless someone misadjusted idle speed. And then I'd have all this vacuum all of a sudden. So it would just allow me to really do a whole lot of advance as soon as I crack the throttle. And by having this vacuum come over, it would overcome the spring, pull the diaphragm back. As it's pulling the diaphragm back, the distributor is rotating this direction. So the distributor is rotating this direction. And by pulling this back, that means that we open the points sooner. One of the issues that we did have on these systems, especially with points, you don't see this with electronic as much, is there was a small wire that connected the breaker plate, which moves back and forth, to the body of the distributor. And that wire could become frayed. And so you'd have cars that ran great until the vacuum advance kicked in, then they'd start misfiring or running rough or cut out altogether. And you would actually, the easiest way to do it is you use the vacuum pump and pulled up vacuum on it and saw if the car started running bad as soon as you advanced it in the bay. If you didn't have a vacuum pump, you could just move the port to manifold vacuum, which you have at idle, and you can see if the car starts running bad. But again, by looking at this, I know by how this diaphragm comes off, the distributor shaft has to what? Turn this way because we're pulling back against it. So we did have vacuum advance. There's also vacuum retard. So some late distributors were actually what we call dual diaphragm distributors, where you would give manifold vacuum to the retard side and ported vacuum to the advance side. And so it just gave it a lot bigger range of control.
Sir Brian,
Yes.
when is the light, because you said advance, when it's light and retard during heavy engine load, when is the light engine load and when is the heavy engine load?
Yeah, okay. So a light engine load would be going down cruising. So I'm cruising down the freeway, you know, not a care in the world. We're doing 60 miles an hour. My gas is barely on the throttle. Now the freeway starts going up a long hill. As it goes up a long hill, I'm still doing 70, but the load is going to increase because I'm having to work harder, right? You're giving it more throttle to do the same speed going up the hill. So that would be a heavier load.
So don't we want to advance at that point?
No, you actually,
Timing on the heavy?
no, you're
Retard
actually
when
gonna
heavy.
you advance up to a point, then you back off just a little bit because as I increase load, I increase heat. So if I over advance with that increased heat, now I get detonation. And so, yeah, you think you want more and more and more, but remember we talked about the difference between torque and horsepower. Advancing gives me horsepower a lot of the time. Retarding gives me that torque. Well, if I have a heavier load, I need the torque more than the horsepower, because if I try to do it too quickly, I just hurt myself. Right? It's like picking up something really heavy. You got to think about it a little bit first.
So it happens automatically when you need
Yeah, it's
light or-
happening. Right. So on a modern car, it happens automatically by the computer. On an old car like this, it happened by how it was tuned, how it was set up. So some of it is the vacuum advance and this. So some of it happens at the manufacturer level. This is how we want to build. But these vacuum advances, we would measure how many degrees we're getting. And some of these had an adjustment in them where you could actually go in there and you had a little Allen, you'd adjust it. Sometimes what I run into a lot is when I buy replacement vacuum advances, they're completely wrong for the car I'm trying to put them on. They advance too little or often too much, which creates problems. So yeah, so all of this was really, so you had the initial design. Hey, we wanted to follow what the book said. It's a factory car. And then you had the, well, wait a minute, I want to go down a quarter mile really, really fast. Or I want to be able to tow my camper and my sand rail up over the mountains to go out to the desert. Right? I'm going to tune that two very different ways. I'm going to manage my timing curve two different ways. Today, what a computer is controlling it based on inputs. So that same truck is going to run great empty as it's going to run great fully loaded. Where back then, because these were set and done, you had to do all that at the tune-up shop or the performance shop where the technician did it because it couldn't adapt. So you kind of set it up. You set a truck that your primary goal with this truck is to go over the mountain and you're going to have less power on the street when it's empty, or you really want that power on the street was empty, but it's not going to tow as good. So it really, you really kind of changed how you built things. Well, today computers are great because they constantly adapt. But since we use these, like these vacuum advances we used up into the 90s, and currently we still smog 1976 and newer vehicles, I have to cover it as part of the curriculum. I'd love to get rid of some of the old stuff. That's why I don't teach L head engines and F head engines, is because they're not in the smog program anymore. I don't need to teach them. So manifold vacuum is obtained through the small hole that we saw in the throttle bore. Venturi vacuum is the vacuum all the way at the top up here, which we only get when my foot's all the way on the floor. So we would use that as a retard signal. And Venturi and the vacuum in each of these systems acts as on the vacuum diagram. Vacuum responds differently in each type of vacuum. And that is really where I wanted to get to today. We'll get into our high tension leads tomorrow. Hello, silly. Someone woke up from her nap and realized I have the door shut. So we're going to get into high tension leads tomorrow, commonly called spark plug leads, and then into spark plugs tomorrow. And I don't want to sell you guys short on spark plugs, because spark plugs is always a great conversation. And matter of fact, the discussion for this module is on a spark plug article. And so spark plugs are always fun to talk about, right up there with oil types and coolant types. It's always a fun discussion. So I look forward to going over that stuff with you tomorrow.